video, we're after a formula for the least square solutions, a method, a recipe, somehow a way of getting it. What we've learned from the last video is if I'm looking for a least square solution for this system, so the closest thing to a solution, I'm going to take any vector x star so that if I multiply a by x star, I don't really get b, but I get the closest thing, so the projection of b onto the column A, which would be the set of all b for which this is consistent. Alright, so this is the theorem that's going to tell us how to find x star. So first, there's a second system. Any solution, let me give you a name, x of the system A. I'm going to multiply that system here by A transpose. We'll see why in the proof, but if I find a solution for this different system, any solution of it is a least square solution for the original system, the one without the A transpose. Alright, so I'm going to need to solve the system. The second part of the theorem tells us that the system A transpose AX equals A transpose B. That system is now consistent regardless of what B was. Is always consistent. No matter what A and B are, as long as the dimensions are right, this is going to work. Alright, so I'm going to have to solve this system. I'm going to get solution, and the solution will be least square solution. So let's just give that system a name, and then we'll prove the theorem. So the system A transpose AX equals A transpose B is called the associated normal system. Alright, so when you multiply by A transpose the whole system, it's a different system, and we'll call it the associated normal system. Yes? Something's weird. Alright, so we're ready to prove this theorem. I'm going to be erasing this definition just so I can keep the theorem as long as I can while I'm proving it. Alright, so I want to find a solution for AX equals the projection. But for now, let's just look at when something's perpendicular to the... So we have the columns, space of A, we have our B, we have a projection and of B, and I want to look at those vectors. So the vector E, I want to see, well, it's supposed to be perpendicular, but I'm just going to take it as any vector. Alright, so let's take any vector E. Okay. Then E is going to be perpendicular to column of A, which is the span of the columns. It's going to be perpendicular to the span of the columns if it's perpendicular to each of the columns. So it must be perpendicular to each of the generator. That's what we looked at in orthogonal set last time. All right, so it must be perpendicular to all of this. That means if I take the dot product of any of them, I should get 0. All right, so these are the columns of A. The columns of A are the rows of A transpose. So E is perpendicular to the rows, same, of A transpose. And so if I multiply E by A transpose, that's going to give us, well, first row, second row, nth row, times E. Those will be the dot product. And so I will get all zeros. Now you can see where A transpose come from. A multiplying by A transpose is really checking, is really killing anything that's perpendicular to the column, and so we're only looking at the parts that's in along the column space, which is why these theorems are true. But let's prove them. Alright, so let's take any x in Rn. Then we're looking for Ax equals the projection on the column space of A, B. That's our goal. That's the system we really want. That's going to be true. Well, this is the part that's along. So I have my B, and I have a projection here. And so this is going to be AX, and so that means if you subtract them, you should get something perpendicular. So if and only if, let me write it as B minus AX is perpendicular to the column space of A. And this is why I did this part. If something is perpendicular to the column space, that means if I take the transpose, I get the transpose of A times it, I get 0. So that means A transpose B minus AX is 0. And if I distribute it, actually let me distribute it before I write that it's equal to 0. So that's A transpose B minus A transpose AX. This is 0, and if I just send the A transpose AX to the other side, I get the second system. Alright, so this is the system we should be looking at, because if we look at this directly, we don't have to take 2 different steps. We don't have, let's say 3 different steps. We don't have to find an orthogonal basis for the column of A, then compute the projection, then solve the system. Instead, we compute this product and this one. We get a new matrix, a new column vector. We solve the system. That's much faster than looking at the projection. Alright, in the next video, we'll be using this to find the least squares solution to a system that's inconsistent.